the technology that we're presenting today addresses the in vitro stage. So you want, I can't point, you want the you want to increase the selectivity of your in vitro stage just before you go into in vivo to save the lives of millions of mice. So in vitro assays, they come in all shapes and sizes. You have very high throughput, very high throughput screens where you can look through a lot of compounds in a short time, and then you have more physiological relevant screens where you can test for a lot of parameters, but your throughput is limited. Our technology is a biologic 3D matrix, which is in the Goldilocks zone, so you get a good compromise between throughput and physiological relevance. So a 3D matrix for cell culture is a sponge that allows cells to grow into them. These cells can be of any type of cell, depending on the disease you're focusing on. So it is advantageous that you have a sponge where you can adjust your porous geometry, adjust your shape, so that you can accommodate big cell types, small cell types, very rapidly proliferating cell types, and very slowly proliferating cell types. So that's just issues concerning the geometry and the form. The material that we're using is hyaluronic acid, which is a component that is present in nearly everywhere in your body, which means that the matrix that you make from this material will have some relevance to any cell in your body, because a neural cell, a cardiomyocyte, a cartilage cell will all have some recognition of hyaluronic acid. When we merge form and matter together, we get a matrix that's very easy to handle in the lab, very easy to analyze further on downstream. So you get a tool that is highly versatile and gives you a very robust setup. We use 3D printing for our fabrication process that allows us to have this great control of geometry. In addition, it also allows us to have a very clean production environment and have a very cost-efficient use of our matrix material, because everything a 3D printer is a syringe dispensing material in predefined lanes. We have so far tested it on neurons and on liver cells. The liver cell is a very commonly used cell for testing for drug toxicity. And we've shown that just on a parameter of cell viability, we are competitive with the leading product on the market, which is Algimatrix from Thermo Fisher. So in summary, we have a technology with a very high potential. We have the product, which is of a composition that is known, that is safe. We have a product that can be sold off the shelf and can be stored in a sterile form. So we've developed it to be a lab tool from the beginning, not an adaptation. It has excellent handling in the bench, which is good for all the drug pharma companies' technicians. And we can make it in all kinds of shapes because we use the process of 3D printing. The 3D printing process in itself is cost efficient, it is scalable, you can make thousands, and it's a robotic process. And it has very, very, very low sample to sample variation, which is crucial for its intended purposes as a reliable assay. We can use it as a as a disease modeling tool. We are currently using for modeling Parkinson's disease. We can use it as a drug toxicity screen, where we are using it with hepatocytes. And what I didn't touch upon is we can use it as a medical device because the components are entirely FDA approved. So this is the potential. And if anything have enticed you, then we welcome you to join us for conversation down at poster 6, and I speak Danish. So, thank you.